So last week was a crypto day, so I didn't get to see you. So let's kind of do a quick kind of recap of where we were and where we're heading to. So last time I saw you, at least in this room, was 2 weeks ago, where we talked about how to use the GKR protocol to construct what's called a PCP, a probabilistically checkable proof. And what's a probabilistically checkable proof? The idea is you take a proof, so take any NP language, let's say that has a proof, like let's say 3SAT, you take a witness or a proof, so a satisfying assignment, and you actually make it longer, okay? So you don't shrink it, you actually extend it, it's bigger, but now to verify it, you don't need to read the entire proof. What you need to do is just read a few locations in this proof. So you can, even though the proof actually became longer, you can verify it much more efficiently by reading just a few locations. And we actually showed how to construct it. How do you get a PCP? And the idea of how to get a PCP, the idea was, well, let's look at the GKR protocol for 3SAT. So let's do a PCP for NP, okay? So any NP you can convert it to a 3SAT. We know 3SAT is NP complete. So convert whatever you want to prove into a 3SAT formula. Now you have a witness. Now what do? You want to generate a PCP. What you do is you pretend you're a GKR prover that has this witness, the satisfying assignment, and want to convince the verifier that this is a valid witness. So what do I mean by run the GKR protocol? What I mean is, let's look at the, so given phi, let's say a 3SAT instance, what you do, you look at the circuit C sub phi that takes as input a satisfying assignment, and outputs, 0 or 1, whether it's satisfying or not. This is a very low depth circuit. It's just as kind of a bunch of checks and add the local checks and add them all together. And now what we do is, how do you generate the PCP given this witness, given this witness for phi? What you do is you run in your head the GKR protocol for this circuit. So remember, the GKR protocol is a protocol that proves that a low depth circuit, that an input is, that a given input, even though it's weird, the verifier doesn't know the input. So it's kind of weird to think of GKR in this context. GKR, the context of GKR was, there's an input, everybody knows the input, the prover and the verifier, but the circuit is large, and the prover wants to convince the verifier that the output is something. Here, it's kind of weird. The input is more or less as large as the circuit, okay, because the checking if a witness at satisfying assignment is valid for 3CNF, not the 3CNF is, the circuit here is almost the same size as the witness, and so it seems like using GKR here is very weird. It doesn't seem like the right application. And in particular, the verifier doesn't even have the input. So how can you use GKR? That seems very counterintuitive. So the idea is, no, let's pretend that he does have the witness. And what do you mean pretend? Oh, don't worry, we'll give it to him. So in the PCP, we'll write the witness. Not only we write the witness, we're going to actually write the low degree extension of the witness in the PCP. Okay, so what is your big proof? It first contains the low degree extension of the witness sitting there. And then now think of the GKR protocol. For each and every kind of question of the verifier, the prover has an answer, write it down in the PCP. So in the PCP, write if the first message of the verifier, the first message is a bunch of first the prover goes first. So you send your univariate polynomial. Then the verifier sends a field element. Now we say, well, if the field element was 1, here's my answer. If the field element was 2, here's my answer. For each and every possible field element, you say the answer. Okay, now there's only polylog number field elements, not so bad. Okay, then you give him the answer. Now, for the prover sends another field element. Now we say, for any possible next message, here's my answer, and so on. So essentially, you kind of open up this GKR to a gigantic tree. Now, first you say, well, this is huge, like it's like exponential. But actually, GKR has a very nice property that the prover's messages actually only depend on the last very few messages of the verifier. So if you remember the GKR, it's a bunch of sum checks protocol. It's like just a sequence of sum checks. And the prover's message depend only on the messages in the last sum check. So it's kind of very few, and kind of where you start, it's very few messages. So to be a little more precise, each prover, in GKR, each prover message depends on the last kind of, what it is, it was log n over log n messages from V, from the verifier, where this is like the number of variables. If you remember when we did GKR, it was a bunch of sum checks, and each sum check was over m or 3m variables. This is the m. And the field is polylog n. And here is the size of the circuit. So think of it the size of the witness, the size of the 3CNF. It's all up to polynomial factors. It doesn't matter. And so now, okay, you need to depend on all these messages from the verifier, but there's only that many in each time. Even if you look, this to the power of this is only poly. That's exactly how we chose H and N, so it will be poly. That's why we chose these weird setting of parameters and not just 2 and log n. But the point is, because GKR has this kind of memoryless property of the prover, you can expand all the GKR into a big proof of size poly n. Now, what does the verifier do? The verifier simply, so that's what the PCP is. The PCP, you write for every possible kind of, you write all the possible answers of the provers and the low degree extension of your witness. That's what the PCP is. How do you verify this PCP? Well, you pretend you're a GKR verifier. You say, okay, let me see your first question. Thank you. Now you're saying, I'm going to choose a random field element, and I'm going to look at the answer corresponding to this field element. And then I'm going to choose my next random field element, and you just kind of go through this kind of tree and randomly and make sure. And at the end, you need to verify. If you remember GKR, at the end, you need to verify. To verify, you need to check your input on a random point in the low degree extension. This is how GKR works. Well, you have the low degree extension sitting there as part of your PCP. So you check that. Okay, that's basically it. Except there's one component that we're missing, and that's going to appear in your PSET, which, by the way, is going to be out this weekend. Okay, so this weekend the PSET is going to be out. Originally, the due date was after Thanksgiving. I'll move it to before, just to give you an incentive to not take it with you on your break. If anybody needs an extension, just let me know, okay? So you'll have almost a month? No, not quite, but close. Okay, but if you need an extension, just let me know. This is very arbitrary. Okay. Okay. So what's the problem? The problem is, so if indeed so what about soundness? Okay, soundness seems like it should follow from just GKR. Okay, you're interacting with like a prover, a GKR prover, and soundness should just follow from the GKR. Except that there's one point here, which is what if the PCP prover doesn't give you a low degree extension of some input? So if he gave you a low degree extension of an input, and this input did not evaluate to 1, namely if he's not satisfying assignment, then this input is not a valid witness because 1 does not exist. In that case, of course, the soundness would really fall from GKR soundness. However, one needs to think there may be a malicious prover who doesn't give you here a low degree extension of some W. So what he should give you, a low degree extension of W, it means like some W goes from F to the M to F, and it's of degree H minus 1 in each variable. Okay, if it's a degree H minus 1 in each variable, then it extends, it's a low degree extension of kind of the W sitting in kind of in, so then W is just W sitting on H to the M. That's kind of the little cube where W is sitting. If indeed he gave you a low degree extension of some W, then you're good. If this W that he gives you is of degree H minus 1 in each variable, then you're good. But what if it's high degree? What if this what if he gives you some W star, which is very high degree, then is it sound? So in the homework, you'll have exactly this. Actually, it's not sound, and you'll ask to find actually an attack. And then there's a way to make sure. So now what the verifier needs to do in addition is to do what is called a low degree test. It's a test that verifies that this W star has low degree. Okay, so this is what the homework assignment, or one part of the homework assignment, is about. Okay, but this is modulo making sure that this is, actually the verifier can't make sure it's low degree, but he can make sure it's close to low degree. So it agrees with some low degree W like on 1 minus epsilon fraction of the points. So you can test that it's very close to low degree. If it's very close to low degree, then most likely, wherever you'll ask, because you ask randomly, it agrees with kind of the low degree, and therefore that's kind of the idea. Okay? But this is the PCP, and the verification just adds a low degree test, and we'll expand on that in the P set. Okay, so that's kind of what we did most of the class. And then we talked about, okay, so now we have a gigantic PCP. It's very large, but you can verify it by looking at very few locations, which is nice. How many locations? Like the communication complexity of the GKR, which on circuits of depth log n, or order log n, which is, for example, 3-sat, then the communication complexity is polylog n. So you can verify this by reading only polylog n locations as opposed to n locations. So it's like an exponential improvement. But again, you have this gigantic PCP. And now the question is, okay, but who's going to note? Here's something to just make sure you understand. It's very important that this PCP is kind of given to the verifier before, if the verifier, so, okay, the PCP is very large. Now, one can say, okay, you know, don't send the PCP. I'll tell you what my queries are. Just give me the answers to my queries. Instead of sending me, anyway, I'm not going to read them, so why send it over? Just send me the answers to my queries. That will not be sound. If the verifier, if the prover gets to choose the answers based on all the queries that he sees, soundness breaks down completely. Okay? And so it's very important that he first tells you what the PCP is, and then you query it. Okay? In particular, what the damaging, the way the cheating prover can cheat is by, you know, when you tell him, give me the PCP in location I. If you ask for it together with location J, it will give you one answer, but if you ask it for location J prime, he will give you another answer. That's how he can cheat. But if he needs to fix it ahead of time, then no, it's one answer, doesn't matter the other locations you ask, and that's what makes this sound. Okay, and you can actually go back to GKR and see, if you use this PCP with GKR, where you give the queries ahead of time, it's like you give the assumption queries all ahead of time, everything breaks down completely. Okay, so it's very important that you first commit it to this entire PCP. And then one can ask, well, if you give this, how does so the entire thing says, look, the verifier is a weak device. That's the idea. He's weak, he cannot do the computation. How can he store this gigantic PCP? So it seems like that's very nice, but how do we use this thing? And the way we use this thing, the way it's used today, these things are used today, and the way they're used is using cryptography. So what we do, we use cryptography to take this gigantic proof and squish it. Okay, and this is used using what's called collision-resistant hash functions. So this is what we're gonna talk about today. We started last time, but we're gonna continue today. But before we go into how we squish it and make kind of everything succinct, let me first, once we use cryptography, we can no longer get soundness against any all-bounded kind of cheating prover, because cryptography can be broken by all powerful adversaries. Cryptography assumes the adversary is not strong enough to break our assumptions. For example, the collision-resistant hash function that we saw, and we'll review it in a second. So now when we talk about proof systems, we need to relax the notion of what we mean by a proof system. By the way, who's scribing today? Ah, okay, great. We need to relax the notion of what we mean by a proof system to what's called a computationally soundproof system. Namely, you cannot cheat, assuming you're polynomially bounded. If you're all powerful and can break my crypto, no guarantees. But as long as you cannot break my crypto, you cannot cheat. So I just wrote it here. This is copied from last time. So instead of interactive proof, we called it an interactive argument. And we say that an interactive argument for some language L, think of it, let's say NP language, but whatever language you want to think about, is a protocol between a prover and a verifier. The completeness is the usual, namely, if X is in the language, then you'll convince the verifier with probability 1. Okay, and if it's an NP and you know witness, you're also efficient. Okay? The soundness, that's where the change is. Instead of soundness, you get some computational version of soundness. And the computational version of soundness says the following. It says, there's some parameter, a security parameter. When you talk in cryptography, there's always a security parameter, which kind of says how much time do we believe real-world adversaries can run in, okay? So what the soundness says, that any real-world cheating prover, real-world meaning it runs in time polynomial in the security parameter. We're going to denote security parameter by lambda throughout this class. Sometimes they call it by n, but n and sometimes k. Here n is going to be input size, so I don't want to. So we're just going to use lambda. So for any p star of size polynomial in the security parameter, he can win only with negligible probability. Namely, there exists a negligible function mu. Again, negligible means it's smaller than any inverse polynomial, such that no matter which security parameter you use, and any x. So think about the p star, he's polynomial in the security parameter. He chooses an x adversarially. The probability, or an x is chosen, okay, it exists for any x. The probability that he convinces, now the protocol depends on the security parameter. So the verifier may choose like a hash function according to the security parameter. So everybody knows the security parameter. Everyone runs in time polynomial in the security parameter. And that's why we give it as input the security parameter in unary. So an input x in this and security parameter, there's a protocol. And the probability that this cheating prover convinces the verifier to accept is this negligible function mu. Okay? So again, we offer soundness only for polylambda cheating provers. Okay, so now you should think of the cheating provers as like a family of provers, one for every lambda. Okay, it's like for any security parameter, you're allowed to give a cheating prover, but they're all, let's say, run in time at most lambda to the n, to the 10. Okay, so polynomial in lambda. Any questions about the review before we go on to the new, to today? Yeah?
So here the prover is not trying to like hide the witness or anything.
No, good. So two things. First of all, we're not at all talking about hiding. Okay, if we didn't want succinctness, you can say the prover will just give you the witness. Here you go, check on your own. Okay, and then, but we'll want another property from these interactive arguments, which is succinctness, or succinctness, or exactly for NP, for example. And yeah.
Does 3 set that meet Boolean formulas?
Yeah, exactly. 3 set is just, think of it. It's exactly just 3 CNFs. You know, it's an and of a bunch of clauses. Each one is like xi1 or xi2 or not xi3.
And can you get the Boolean formula with small enough depth?
Yeah. So any 3 CNF is of the form like clause 1 and clause 2 and clause n. Let's say you can get a Boolean formula with fan-in 2 of size order log m. Because you just do kind of the and, all the ands, and then you have these little literals at the bottom, and each one is constant size. It just depends. Each clause is constant size. So it's really a log m circuit. Okay, so you can take any 3 set, which is just an and of a bunch of literals, and write it as a log depth circuit.
So can you go directly to some J and do the PCP over some J by doing the argumentization instead of going through GKR?
okay, to get a PCP, I need to go, the way I construct the PCP is by going through GKR. I do a GKR on this kind of circuit. I open up all the possible prover's messages, and that's what constitutes the PCP, in addition to the low-degree extension of the input. That's going to be the PCP. And the verifier just kind of verifies, behaves like the GKR verifier, and checks that the witness he gets, the extended witness, is of low degree. Like it does a low degree test. With the low degree test we didn't talk about, but it's going to be in the homework. So that's how the PCP works. And now I'm kind of talking about how you use this long PCP together with cryptography to get these succinct arguments. That's kind of the next step. How to use cryptography to just have like a fully succinct protocol. Let's say for NP, we want a protocol that has polylog communication. Okay, so you have an instance of length n, and the prover wants to prove to the verifier that x is in the language, and you want the communication to be only polylog n, for example. Okay. Okay, one thing I do, oh, did you have a question?
It's just like a quick, like, I'm thinking like, is the interactive protocol necessary? Because in like the traditional, like the complexity theory PCP, the W has to be written down in advance and not be, and it cannot be adapted. Like,
right, right.
So it's the whole point of the protocol trying to like fix some problem in a sense where you are forcing the prover to commit. To
exactly, exactly. Okay. That's exactly it. That's exactly it. Exactly. One thing I do want to say, note that I asked for the cheating prover to be polynomial in lambda, okay? Because usually that's what my assumptions usually look like. I want to say if I use collision resistant, I would say, well, I use some collision resistant function with security parameter lambda. It says that my assumption is that a poly lambda size circuit cannot find collisions. Okay, my cryptographic assumption usually assumes that they're hard to break against provers, against adversaries that run in time poly lambda. But this may seem very weird and very weak. Why? Because our goal is to come up with succinct arguments. Okay, succinct. In particular, one example to keep in mind is, let's say the input n can be really huge, but I want the communication complexity to be polylog n. So think of lambda as being like polylog n. Okay, everything's going to grow with the security parameter. But let's take the security parameter to be polylog n. Now, it seems weird. You're like, wait, really? So the cheating prover, if the instance is of length n, and the security parameters of length polylog n, the cheating prover, we're not even giving him the opportunity to read the input. So it's a very weak guarantee. So what does this guarantee tell you? Let's say I want you to prove to me that a given x is in the language. And my only guarantee is if you run in time, that's only polylogarithmic in n, you can't cheat. Okay, well, what if you run in time n? So that seems like a problem. Especially if n is too big for anyone to read, then in some sense, why, nobody's going to use it anyway. And if n we're able to read it, if I'm able to read it, then you have the time to run in that time, so you run in time n. I'm not going to assume you run in time polylog n. So this seems very weird. Okay, you should not be happy at this point. You'd be like, wait, something is going on. I don't like this definition. It's meaningless. Like this, if you don't want succinctness, you can make lambda be size of n, and then you're happy. If lambda is of size x, like the instance size, then you can say, yeah, the instance size is some n. I allow my honest prover runs in time poly n. I allow my malicious prover to run in time poly n, and that makes sense to me. But now I'm saying, no, the honest prover, he can actually run in time n. The malicious cannot. No, the malicious usually has more power than the honest. So it's really a weak guarantee that kind of, especially if we want to take the security number. The idea is we're going to take the security number really small. Okay, really, really small. But if we take the security number so small, we should give the adversary more power than poly in the security parameter. Because it just doesn't meet real life. The idea of this is to kind of capture real life setting, not to make a model that makes no sense. So if we take lambda to be very, very small, then the actually real world adversary can run in time more than poly lambda. They can run in time poly n. So it doesn't capture. Yeah?
If P star is a circuit, how do we even think of plugging in like a variable length X into a circuit?
They can't even read X. You're right. Yeah, for example.
Not even well defined.
So you can say, P star can't read X. You're right. They can't read X. It's a circuit, and yeah, it can't read X. This is a big problem. Okay, so the way I defined it is really doesn't make much sense. Yeah.
Just to make sure, why did we need lambda to be polylog n? Is it so that the resulting interaction is succinct enough?
Exactly. So great question. The question is, why do we need it to be polylog n? So what I think where maybe you're going to say, let's make lambda n to the epsilon. For a constant epsilon, n to the 0.001. Then the communication complexity, then we say, look, the original proof grows with lambda, which is n to the power of 0.001, which is much smaller than n, so we're still happy. But the cheating prover can run time any polynomial in it, so it's poly n. So that's good, you're right, and that's a good setting to think about. In that case, there's no issues. So one thing which you're saying is, let me fix all your problems. Just take lambda to be, think of it as n to the 0.01, and you're done. Or n to the epsilon, and you're done. Okay, if you think about n to the epsilon, everything kind of makes sense. You allow the cheating prover to run in time poly n, the instance is n, and we're good. Okay, so that's one way to think about it. So usually the way we think about it, we say for any n, we choose a security parameter that depends on n. Okay, that's usually how we do it. We have an n, and now we say, okay, which security parameter do we use? It's kind of a function of n. So that's one example. Choose that security parameter, and then you solved all the problems. But what if I want more succinctness than that? Maybe n to the 0.01 is not, it's okay, but I want better. I want polylog n. So what if my lambda, that's one option, but another option is polylog n. That's even more succinct. So that's what I want. Now you're saying, well, if that's what you want, you get a definition that makes no sense. And you're right. But then what I can do is strengthen the definition. So how do I strengthen the definition? I'm going to say, you know what? Poly is one option, but let me actually make a stronger cryptographic assumption. I'm going to assume, sometimes I'm going to say for any adversary that runs, for any P star that executes a circuit, not of size poly lambda, but of size 2 to the lambda to the epsilon. I'm going to allow my adversary to run in time 2 to the lambda to the epsilon, more than poly. Now it's a stronger assumption. Okay, so now I want to say an adversary that runs in time 2 or of size 2 to the lambda to the epsilon cannot break my hash function. He cannot find collisions. It's a stronger assumption. But now this makes sense. So I can take lambda very, very small, but I'm saying even if the adversary runs in time that's much bigger than lambda, that's actually 2 to the lambda to the epsilon, even he cannot break my crypto. And that's why when we talk about succinct proofs, most often we talk about this kind of assumption, like sub-exponential assumptions come up a lot. Okay, and we'll see that actually. But often, if we want to implement, if we want to take lambda to be polylog n, it makes sense to require for the soundness to make sense, to correspond to real world applications. It makes sense to require sub-exponential assumptions of our underlying cryptography. Okay, so just to kind of close this parenthesis, one can talk about poly-size cheating provers. It will give you a more standard assumption, but the soundness guarantee you get may not be strong enough depending on how security parameter relates to the input size. If you want lambda to be the security parameter to be very, very small, and yet you want to offer security against adversaries that run in time poly n, then you will need to make your assumption stronger. Okay? But given, this is kind of at the end a design choice. Okay? For now, we're just going to think of, for any given P star of size poly lambda or more, I don't know, whatever we choose here, that corresponds to the assumption. Okay, so if we have a T-secure assumption, then for any t size, so in general, more generally, you can replace this by t of lambda. Right, any t, it can be poly, it can be sub-exponential, it can be whatever. Okay, and then we choose the t, and now the t kind of governs the application, but once we have a t, now we can just prove it using math. We don't need to think about it anymore. Okay, so that's kind of how lambda relates to n, okay, and how the strength of the assumption relates to n. Okay, any questions about that? Okay, so now let's go ahead with how we use, so that's what we want. I want to come up with a succinct interactive argument for all of NP. Okay, I want to show how I can take any NP language. Let's think of 3-sat, why not? It's complete. I want to prove to you that a 3CNF formula is satisfiable. I have a witness of length n. I want to prove to you that it's satisfiable, but where the communication I want it to grow only with lambda. Okay, lambda can be polylog n. I don't even don't go now to the choice how we chose the lambda. But now I have a security parameter lambda. I want the communication to only go with the security parameter, not with n. Okay, so how do I do it? So the idea is, well, I'll use my PCP. I have my PCP. I'm going to use crypto to squeeze it. How do I use crypto to squeeze it? It's exactly what collision-resistant hash functions do. They take a big thing and they squish them down. So now I'll take my PCP. The prover will take his PCP. He will squish it down using a collision-resistant hash function. Okay, so he gives the verifier. Here you go. Here's like a squish, like a digest, you know, of this PCP. Okay, the verifier takes this thing. It has no meaning. So what does he do? Now he says to the prover, okay, thank you very much, but I want to see the PCP on a few locations. So now what can the prover do? The prover can't. Okay, so collision-resistant hash function as is, it's a way to kind of compress in a way that you're kind of committed. Because you can't find collisions later. So you can't open, you can't kind of, after you gave the hash value, you can't open to x and x prime. You can't give x and x prime that both hash to the same value. But I don't want you to give, you can't give me, now you're hashing an entire PCP. The PCP is big. You can't just, I never want you to give me the verifier, never want to receive this PCP. I can't even hold it. I want to receive a few bits of the input. So what we need is a collision-resistant hash that has a special property that you can open bit by bit. So instead of giving me the entire kind of input, the entire pre-image of the hash value, I want you just to give me a few bits here, a few bits here, and a few bits here. And prove to me that they correspond to the input you hashed. So now I'm going to define this primitive. Once I have this, we're going to see it's going to be very easy to come up with the actual interactive argument. Okay, so the primitive is what's called a collision-resistant hash with local opening. Let me define it. So we're going to have a collision-resistant hash function with local opening. And this consists of 5 algorithms. The first two are Gen and Eval. These two algorithms is what defines collision-resistant hash function. So this we saw last time. I'll just repeat it just to recall. Gen takes as input a 1 to the lambda, the security parameter, and outputs hash key. So this is some key. Eval takes as input hash key, and any input x from 0, 1 star, anything, okay, any string of any length, and it outputs a hash value. We'll denote it v, and that's fixed in 0, 1 to the lambda. I call sometimes delta and sometimes lambda, right? Sorry, it's lambda. You output a hash of a fixed size, which means you can take very, very long things and you digest them down to a value of size lambda. Okay, so it takes an input of arbitrary size, can be huge, can be 2 lambda, 4 lambda, ton, huge. And it digests down to a string of size of length lambda. Okay, now there's 2 more algorithms, 2 or 3, okay. So now there's an algorithm called open. Open, I just want to make sure, I want to tell me, don't give me the entire, I want to, so V is just a digest, has no meaning. I want to tell you now, I want the ith bit of x. Don't give me all of x, what you hashed. I can't hold it, I just want the ith bit. So open, so what do? You open, how do you open? You have the hash key, you have x, which you computed the value v, and now you have some I in kind of 0, 1 to the length of x. So this is kind of which index I want you to open. And what you output is a bit b, which is kind of correspond to xi, the ith bit, a bit, and an opening value, row. Okay, this is some kind of string, and this is of size lambda, so small. Or it can be poly lambda. Okay, an opening of size poly lambda, yes?
In this definition, who's running the open?
Good. Who's running the open? Good. The person who generated the hash. So let's say you're the prover. You want to prove to me that phi is satisfiable. You generate a PCP. I don't want your PCP. It's too big. You give me a hash, a value v. Thank you very much. Now I want you to open the PCP and some location I. So I tell you, here's I. I don't know your PCP. I don't know your input. You give me some row I. Like an open, give me xi. If you only give me xi, you can cheat. You can give me whatever you want. I don't believe you. So I want you to give me kind of row I. This opening is like a proof that indeed what I hashed down in the ith location is sitting xi. This is what you think of row I. It's like a proof. Yeah?
Shouldn't I be in like log of
Oh, sorry. Thank you. Sorry. It's an index, not in 0, 1, sorry. It's an index with 1 until the length of x, 1 to n, let's say. Yeah, thank you very much. Questions? Yeah?
It isn't so much a question, it's just like, I guess it's just interesting that you have to retain the entire hash value x. Like maybe that's necessary for correctness to be able to confirm any bit of x, but I don't know, it just seems interesting that in practice you would have to keep storing all of these hash values.
Right, so wait, let me make sure what your comment is, note that to open, you need to know the entire x. And why do you need to know the entire x in a sense? To open to bit I. So in some sense, look, I mean, to open to bit I, all you need to remember is row I. That's kind of what you need to give for the opening. But all the row I's together contain all the x. So that's why you need to kind of store all the x. And you'll see the construction soon, so it'll be kind of clear. Okay, the last algorithm is what we call verify. And verify takes as input a hash key, a hash value. So now I'm verifying. You gave me xi and row I. How do I know it's good? So I take my hash key, the value that you gave me, I, xi, and row I, and this algorithm outputs 0 or 1, namely accept or reject. Okay, so I can kind of verify whether the row is a valid opening. Okay? And now what are the guarantees? So you can hash and then you can open. Like what is the guarantee? The guarantee is, first of all, if you do everything honestly, I'll accept you. Okay, so there's 2 guarantees. The first guarantee is just correctness. And the second guarantee we want is collision resistant. So we'll see. So for correctness, before actually, let me just say, these are all PPT algorithms. Okay, all of them are polynomial time. Actually, everything is, these are polytime algorithm, and this is PPT. So this is a randomized algorithm, polytime. So it runs in time polylambda, generates a hash key. These are all deterministic algorithms. Okay, they run in polytime. So eval takes his input x, he runs in time x, of course. Open runs in time x, but verify runs in time polylambda. Why? Because hash key is of size polylambda. This is of size lambda because I required it. And xi is a bit, and this is of size polylambda because I required it. So the verifier runs in time polylambda. Okay, so when you send me a hash value, I get a value of size lambda. When I want you to open to a certain bit, I can check it in time polylambda, independent of n. I mean, lambda may depend on n, but it doesn't grow with n. Yes?
Why is eval not allowed to be probabilistic?
Why is eval is not, these are polynomial time.
Why is not allowed?
Why is it not allowed? It doesn't need to be. It just doesn't need to be probabilistic. I'm not inherently opposed to using randomness in algorithms, but it just doesn't need to be. Whereas Gen has to be probabilistic. Okay, great. Thanks. Good question. Okay. So the correctness guarantee just says that, let's see, for every lambda, every hash key generated, like in the image of Gen, and every x, okay, not every x, we get completeness up to x in 0, 1 to the 2 to the lambda. Okay, so or I should say, sorry, smaller or equal to 2 to the lambda. So let's think of the security parameter. It says least of size log n. N is the size of x. Okay, we never take security parameter to be smaller than log n. Okay, and so that's why, like, we always assume that the size of x is at most 2 to the security parameter, the number of bits in x. Okay, so for every x, what we want that the probability that verify, oh, I forgot to say, for every I, the probability that verify on hk eval hk of x, this is v. What else do I have? I, xi, and rho I, which is open. This is kind of the row. It outputs 1 with probability 1. So if you were honest, you take some input x, any hash key, and you give me a hash value, and then you open it, I'll accept you. Okay, if everyone's doing what they're supposed to do for any x, and for any hash key, we'll get output 1. By the way, sometimes one can define it also with high probability over randomly choosing a hash key, but our constructions work often in the worst case. But one can also, a weaker definition is for kind of hash key randomly generated. And here you have 1 minus negligible, where the probability is over the hash key. Here actually, sorry, here there was no, okay, before there were no probabilities because I just chose for every. But one can think of a hash key randomly generated, and you can have a negligible probability of error. We won't need that because this, I mean, some schemes, but many schemes are just probably 1. Yeah?
So, like, you mean that correctness always holds for any hash key, but soundness needs the randomness, right?
Right, yeah, I didn't go to soundness yet. Yeah. We'll see soundness in a minute, but correctness we can get for every hash key, but one can think of constructions that actually it's only, even correctness with high probability, but often we think of it as correctness 1, yes?
For correctness, you have that restriction on x?
Again?
Why for correctness you have that restriction on the length of x?
Okay.
See, the length should be less than 2
Yeah.
lambda, right?
Yeah. You're asking why?
Yeah.
Because our constructions, often we'll see a construction, and we'll see that if the length is okay, the reason is our constructions grow with log x. That's the truth. It just grows with log x. And we want the output to be lambda. So the fact of the matter is the way we construct these schemes, our construction, the hash value grows with log x. But we don't want to kind of say it. We want to just say lambda because it's nicer. So we just make sure lambda is at least log x, and then we're OK. OK, great question. OK, any other questions before we go to soundness? OK, so soundness, that's the more interesting one. Soundness says, intuitively, that for any bounded polylambda or t-bounded, if there's some, you have some, the soundness is like, you can call it t-soundness. Okay, and t, you can think of poly-soundness, you can think of 2 to the lambda to the epsilon soundness, but there's some t-soundness, and it says any adversary that runs in time at most, of size at most t, the probability that it can find a value and an index, a hash value and an index, so that in that index he can successfully open to both 0 and 1 is negligible. Okay, so it essentially means once the adversary gave you a hash value, for any index, he cannot generate a valid opening both for 0 and for 1. It's impossible for him. Okay, so let me write it formally. So for any poly t, again, think of t as like linear, so poly lambda, poly t size adversary, the probability, and the probability is over hash key. He gets a random hash key chosen by Jen. Okay, gets a random hash key chosen by Jen. This adversary, given the hash key, he tries to open some index in 2 different ways. So his goal is to give you a hash value v, an index I, and a valid opening row 0 that opens to 0, and a valid opening row 1 that opens to 1. That's what he outputs. So the adversary outputs, he gets a hash key, he outputs a hash value, an index, and 2 opening for that index. That's what he's trying to do. 1 corresponding to 0, 1 corresponding to 1. And the probability that both of them are valid opening, the probability that for every b in 0, 1, verify agrees, so verify given hash key v, I, and a 0, b, and row b outputs 1, this is negligible. Okay, so again, soundness is like collision resistance in this setting. So this is kind of another way to, usually people call this property collision resistance. And the collision resistance property says that once the adversary chose a hash value, the probability that for any index, okay, he chooses for any index I, the probability that he can open in a way that verifies in an accepting way to both 0 and 1, so for every b, row b is a valid opening, row 0 is a valid opening for 0, and row 1 is a valid opening for 1, that happens with negligible probability. Okay, so for every row, there exists negligible, such that. Okay, so this is the collision resistant property. Any questions about the property? Okay, so now I have 2 things I want to do. The first thing, unordered, 2 things I want to do. One is show you how you construct this thing. And 2, show you how to use it to construct an interactive argument. Any preference on the order? What goes first? Who wants construction first? Who wants interactive argument first? Okay, we'll do interactive argument and then we do construction. It was not that. If anybody wants to weigh in, say so, because it wasn't very significant, the result, but okay, so interactive argument first? Yeah, okay. Okay, so here's this is what's known as the Kilian-Micali protocol. Okay. Okay, so actually I want succinct interactive arguments for NP. Okay, so I'm going to show you how to construct a succinct interactive argument for any NP language. Okay? So here's how I'm going to do it. The prover, first, so we have a prover and a verifier, and here's what they both share a witness X. The prover wants to prove to the verifier that X is in the language, and he has some witness. Okay, and you can think about it as a 3CNF. Because we talked about 3CNF, it's definitely complete anyway. It can be nice to have like something concrete in mind, so you can think about X as being a 3CNF and W as satisfying assignment. Okay, what does the prover do? The first thing, any guess what the prover first does? Thank you. Compute the PCP, that's the first thing he does. So he takes W and converts it to a PCP. Okay, and if you want to have something concrete in mind, he opens all the GKR, adds a low degree extension of the witness. That's a huge thing, that's a PCP. He can't ship it over, that's too big. What does he want to do instead? Hash. Okay. He needs a hash key. He's like, I want a hash. Can anybody give me a hash key, right? Oh, sorry, because it's an argument, I should say they also share security parameter. So the first thing the verifier does is he says, sure, here's a hash key, I'm gonna generate it. And here you go. Now what does the prover do? Hash, thank you very much. So I compute, he sends over V. We usually didn't, okay, he sends V, which is eval of hash key and the PCP, pi. Okay, so the verifier gets this V, this digest. It's a bunch of bits with no meaning. He wants to open this PCP, right? Okay, so what does he do? Well, what does the verifier gets the V, doesn't understand a thing. What does he want from the prover? What will he ask the prover? Exactly. He randomly selects a bit and has to open it. Which distribution? How will he choose which bits to open from this PCP?
So whenever the PCP asks to correlate the oracle, right?
Exactly. What the PCP as the PCP verifier. So what he does, he runs the VPCP, and the PCP verifier tells him, oh, sure, ask I1 up to, I don't know, some IL. So, okay, let me just mention, sorry, I'm going to construct an interactive argument for NP from two ingredients. Yeah? One, I'm going to use a PCP. So we have a PCP in our head, the GKR PCP. Yeah, we have it. And two, this collision-resistant hash with local opening. These are two ingredients that we're going to use in this construction. And we're going to assume, remember when we talked about PCP when we defined it, it was like before we went to kind of crypto land, and we said there's two parameters, CNS, completeness and soundness. We said that a PCP, it comes with two parameters, completeness and soundness, CNS. And Usually we think of the completeness as 1 because all our PCPs have actually completeness 1. That's kind of, it's easy to construct them with completeness 1. Soundness, we pay for soundness. So the more queries you get, the better soundness you get. And here we're going to always assume that the soundness is negligible. Okay, so we give enough. So for example, if we do one GKR, if you just run the GKR verifier once, if you remember, you kind of query 1 point in the low degree extension, but a field element in GKR is of size 1 over polylog. So the soundness you'll get, the field size is polylog. So the soundness you'll get is 1 over polylog, which is pretty not great. I want negligible. So I'll need to repeat the GKR enough times, like log times, so that it will become negligible. I want my soundness to become negligible. The reason I want the soundness of the PCP to be negligible is because when we defined interactive arguments, we wanted soundness to be negligible. Okay, and these two will kind of, the soundness I get from my interactive argument will kind of depend on the soundness I'm going to get from my PCP. So I'm going to assume here that I have a PCP with negligible soundness, that I ask, so if I have a PCP with soundness half, I'll just repeat it polylog, like I'll repeat it, let's say lambda times, and now my soundness becomes 1 over 2 to the lambda. Okay, so I'm going to always assume that it's negligible in lambda. Okay, so I run the PCP verifier. Yeah?
Wasn't the previous version succinct minus the oracle access to the proof?
What do you mean? What is the previous version?
The previous version where you had to query the proof oracle.
Okay, so when you had, okay, so you said, let's remember the PCP model, where I had the PCP as an oracle, and I queried it. That was very succinct. But if I had an oracle, in which world do I have an oracle? Well, this oracle is a nice, like, who puts the PCP in the sky for me? Where's the sky? It's not sitting on a cloud. You know, it's like a, well, cloud, I guess, now has many meanings. But, you know, so it can be sitting actually on a cloud. But that's kind of the point. We don't want anyone to store this PCP. We don't want to assume someone actually holds this thing. So in that model where you assume you have an oracle, everything is succinct. Now what I'm trying to do here is get rid of that assumption that I have an oracle. Great, yeah?
What about even before the PCP? If you were to just do interactive GKR on this circuit?
Okay, good, good, great, great. So the question is, look, just do an interactive GKR in the circuit and this C sub phi that's maybe here. Oh no, it vanished. You can, but here's the problem. You can do GKR, and essentially it's what we're doing in the PCP in some sense, but here's the issue. But you're saying GKR, you don't need to deal with the hashing, right? That's kind of your point. Very, very good point. However, in GKR, anybody see, that's actually a good, anybody see what's wrong? So let me repeat your point. The point is the following. Look, GKR is succinct. Think of 3-sat. It's very low depth. It's succinct. The communication is very succinct. Why are you now going to crypto and opening GKR? Just do GKR and be done with it. Why are we doing all of this? Very good. Why? Because GKR works if the verifier knows the witness. If the verifier knows the input. In GKR, when we talked about GKR, we said, look, the verifier and prover both hold an input. And the verifier wants to know the output of this circuit and the input that he has.
Okay.
And indeed, at the end, the verifier needs to check the final thing against his input. You know, is in the end going to get kind of a value in the low degree extension, and he checks, oh, is this consistent with the input I have in my hand? Now he doesn't have an input. So what do? So actually, let me tell you something. The way these things are actually implemented, it's a very interesting thing to say that, because the way they're implemented is actually more along what you said. What they do is, first, they commit to just the witness. You're saying, why are you committing to the entire PCP? You have a witness, commit to that. Or commit to the low degree extension of the witness. And actually, in practice, that's what they do. They only commit to the low degree extension. And then they apply this interactive GKR, or now they have even better protocols, IOPs. But that's for another time.
So you're saying once you can make the witness, then you do normal GKR, and then you can only need to open the bits in the witness that you care about.
Exactly. So what you can do, you can first, the prover can tell the verifier, sorry, the verifier tells the prover, I know you claim that you have a satisfying assignment. Give me a low degree extension of your assignment, but hash it down because I don't want to hold this entire thing. Now I have a hash. Now we're going to do GKR. Do GKR. Then I need to check a random point in the a random point in the low degree extension. I'll ask the prover now open, but now you're committed ahead of time.
And then you have to make sure it's low degree.
You need to add a low degree test to it. Yeah, exactly. So many of the implementations, that's exactly how they work. And actually a lot of the work currently in the last couple of years is actually not so much on improving GK, that too, but a lot of the work is actually on the commitment. How do you construct this commitment that's kind of the most efficient and so on? Okay, great. So yeah.
Do we not give the verifier the witness because the witness is too large?
Exactly, exactly. We don't want to give the verifier the witness because it's too large.
So we don't have like zero knowledge properties?
I don't care now about zero knowledge. Usually when people implement this, they add zero knowledge on top, kind of as a, but for now, I don't care at all about hiding. I just want verification, like just to verify correctness. Yeah, no, like all of the hiding zero knowledge is kind of orthogonal. Yeah.
So the commitment that's given to the verifier is only used for verification. It's never actually open.
It's never opened completely. Yeah, it's never, good point. So what you're saying, this hash will never be completely opened. Okay, so the prover computes this PCP, he sends it over. The PCP will never be opened in its entirety. It's too big. Or the witness, never going to be open in its entirety. Instead, what happens is the verifier generates PCP queries, and he sends the PCP queries, I1 up to IL. And what the prover does, he only opens the locations pi I1 up to pi IL. So he only gives him the PCP and these locations. And opening, row I1 up to row IL. Yeah?
This is a minor detail, but it was mentioned before that if you query like everything in parallel, sometimes it's not sound. Can these be sent at the same time, or would they have to be sent like through multiple sequential rounds?
Okay, so if you do a PCP, then they can be sent exactly at the same time because the PCP was committed to the PCP and we're done. If you do GCAR, you need to do everything sequentially.
Right, okay.
Yeah, if you did the version that was proposed here where you don't do PCP at all. You hash your witness and then you need to do GKR completely interactive. But if you have a PCP, then it's committed. Now you don't have to do anything sequentially. That's it. The guy is kind of stuck. So you can do everything at the same time. So great. So you send all the queries, you get back the answers. What does the verifier do? How does he decide if to accept or reject? What tests does the verifier do? Yeah. Fantastic, exactly. What does he do? He runs two things. He runs the PCP verifier with kind of I1, IL, pi I1 up to pi IL with X also, X comma, and checks that it's 1. And it also checks all the openings. So he checks that verify of hash key V ij pi ij row ij equals 1 for every j. Pi ij is kind of, no, because when you verify a PCP, okay, the verifier never knows the entire pi. He never reads the entire pi. But the verifier, of course, he needs to know the instance. Like you need to check it against the instance. So the proof is succinct, but the verifier's work, he has to read what the claim is. Okay, so the verifier will run in time linear in X. That he needs to read what the claim is. But the communication is very small. So the communication is hash key, which is probably security parameter, V, which is security parameter, I1 up to IL, which is going to be at most security parameter, and the opening, which is security parameter. So everything here only grows with the security parameter. Okay, polynomial with security parameter, not with x. So if the security parameter is polylog n being the length of x, then you have communication polylog n. To verify, well, okay, this verification is of size polylog n, like security parameter, because the x doesn't come in. But of course, to verify the PCP, you need to read the input. You need to read what the claim you're verifying. So here you do run in time linear. In these PCPs, usually the runtime of the verifier is linear in the input length. And let me mention, actually, there's this notion, which we won't go into this semester, but it's called PCP of proximity, where the verifier doesn't even need to read the input. He just reads a little bit. But now, of course, if he only reads a little bit, then how does he know that the input is correct? Maybe he didn't read one bit, and that flips it from true to false, you know? So the only guarantee he has that if he's accepted, then this input is close to an input in the language. That's why the proximity. So there is a notion where the verifier is actually sublinear in x. He runs in time much less than x, but then the guarantee is weaker. The soundness guarantee is weaker. The soundness just says that if you accept, you cannot accept statements which are far from being in the language, but you may accept claims that are false, but close to ones that are in the language. So it's a proximity type soundness guarantee. But if you really want soundness, yes or no, you have to read the input. There's nothing, nothing you can do. Unless the input is kind of in an error-correcting code, or you change something about the model, but otherwise you have to read the input. Any questions about the construction? Forget about soundness and so on. Just about about the proof, just about the construction. Okay, so I just want to point to one thing, that I said let's send I1 up to IL. Really, the way the PCP verifier works is he gets his input, like let's say the security parameter, just to know how many times to repeat if the original PCP, let's say, is of size, has soundness half, he needs to know how many times he needs to repeat it. So there's some security parameter. And some random, he also knows the input length, like n in binary. So this can be very efficient. And he uses randomness. My point is, instead of sending I1 up to IL, instead, he could have just sent the randomness. Okay, he could have sent the randomness and tell the prover, okay, you see this randomness? Compute, run this yourself. Okay, why am I saying this? So it's like, okay, fine. Like, why is that interesting? The reason this is very interesting is because, and also here, by the way, here instead of this is a randomized algorithm. Actually, here it's not important. Let's just leave this as is. I want to focus on this here. Why is this important? Because later, not today, but later in this class, we'll start actually next week, we'll see that we'll want to go, after we'll prove this and we'll be very happy and we'll say, wow, we have a succinct argument and it's so succinct, we can have all the security parameter, success, happiness. But then, of course, every time we have something, we want some more. And then we'll say, you know what? We don't want interaction. Why interaction? We want to go back to kind of actual proofs. So we'll want to eliminate interaction. And what we'll see is a way to eliminate interaction from protocols where the verifier's messages are completely random. Okay? And that's why I want you to remember in your head that here this message can be completely random. Okay, we can make also this random, but we don't need to because it's the first message. It's kind of, the first message is kind of special in that it's kind of the first one, so we don't need to kind of eliminate interaction from it. It's kind of the first one. So that's fine. All the later messages of the verifier will need to, if they're really random, just random bits, then we can show how we can eliminate an interaction, that we can actually get rid of the interaction. So I just want to point out, this message is completely random. These I1 tile are not random. They're actually correlated. But you can just send the randomness. Yes?
I mind, but why is the first message special? Because you should imagine that, like, I don't know, there could exist some particular hash key which is really bad or something. So if you, like, it feels like you should still be sampling the first hash key.
Oh, you're definitely sampling it. No, you're going to sample this hash key for sure. I'm just saying the hash key itself is not necessarily random bits. Depends on the hash. Some hash keys are random. Some hash keys have some structure, depending on which hash function you use. So some hash keys are just random, and then this message is just random. Some hash keys are not random. I have like, I don't know, LWE structure, for those who know what LWE is, but I have some special structure. So now I'm saying, I guess what I was saying is, if the messages from the verifier to the prover were truly random, we're going to see we can eliminate interaction. So I'm telling you, just notice it's completely random. And now you can say, wait, this is not necessarily random. I don't know how hash key is distributed, depending on the construction. Maybe it's not completely random. Then I say, don't worry, this doesn't have to be, it can be an arbitrary distribution.
But I guess since Gen is already random, why can't you just send the coins you
Good. So you're saying, hey, send the coins here too. Why instead do the same. Put here R and send R. You can, however, not all hash functions, there may be hash functions that are secure if you only give the hash key, but are not secure if you give the randomness used to generate the hash key. Maybe with this randomness you can break the collision resistance. So some hash functions are okay, some are not. Like the hash function that we'll construct, you'll see, is fine. Actually, it's randomness. But that's under specific assumption, and some are not. It's not okay to give the randomness. But I just want to point out that for later to eliminate interaction using what's called the Fiat-Shamir paradigm, we'll talk about it next class, the first message actually doesn't need to be even random. It's only the later messages have to be random. So I just want to emphasize this is random. There were other questions? Yeah?
The verifier, like what is n? Like what is
n is the size of x, yeah. So, sorry, I said here, yeah, n, thank you, is the length of x. Thanks. So the PCP verifier needs to know the length of the instance he's working with to know which queries to ask. Yeah, Tina.
The instance given in binary when the security parameter is given in generation?
Because, yeah, good. So I just want to emphasize that to generate these queries, you don't need to run in time that's polynomial in n. It's enough to run in time polylog n in order to generate the queries. That's why I gave it in. It doesn't matter so much because here anyway you need to run in time linear. So you're like, why am I making this point? Yeah, it's not very important. Even though sometimes it is important when later you want to talk about proximity and stuff, then all of a sudden it becomes an issue. So yeah, this is just to emphasize that the PCP verifier, at least when generating the queries, doesn't run in time linear in n. It runs in time actually linear in security parameter and polylog in n to generate the queries. Okay, questions? Okay, so let's go ahead and prove the, let me see, change the order, so I just want to make sure I'm not skipping. Okay, yeah, let's do it. Okay, soundness, completeness, let's analyze this. So I want to prove that it's complete and sound, this protocol. Yeah, so fix an NP language, your favorite one, let's say 3SAT. And I want to argue that, if the prover is honest, he indeed has a satisfying assignment or a witness, the verifier will accept him with probability 1. And if he's honest, he does everything like he should. And if in the soundness, if he tries to cheat and gives me an X not in the language, we're going to catch him. He's going to be accepted with probability negligible. Okay, so that's the goal. Any questions before we? No? Okay, so let's do it. So, okay, let's start with completeness because that's really easy. The focus, well, I can just say completeness is not worth writing because it's so trivial. So what do I want? What does completeness say? Completeness says if the prover chooses X's in the language and he has a witness, he's going to be accepted with probability 1. Why? Why is he going to be accepted? Well, let's see what he does. He chooses a PCP. The PCP, let's say, has completeness 1. That's my assumption. It's soundness negligible and completeness 1. Okay, I assume that about my PCP. Otherwise, the completeness is like the completeness of the PCP. So he chooses a PCP, he hashes it. Now he gets PCP queries from the verifier. He opens the PCP. Now these are accepted with probability 1. Now he generates also open. These rows are from open, right? So I didn't write it, but row ij is by computing open on hash key pi ij. Right? That's how he generates row ij. And what do we know? We know by completeness here, or correctness, like he's accepted with probability 1. So the probability that both the PCP is accepted, the PCP verifier accepts, and the hash verifier accepts is 1, because both of them is 1. I took perfect completeness for both of them, so it's just, that's all we do. So this is just pretty trivial. Yeah, questions? Are you guys okay moving to the soundness? That's kind of the interesting part? Okay. So how about soundness? Okay, so what's the idea? The idea for soundness is the following. I want to say, so suppose there exists a cheating prover that chooses X not in the language, okay, and manages to cheat. So let's suppose, and let's try to break the collision resistance. Okay, so suppose there exists t time, whatever. Okay, we assume this is with t soundness or security, and I call C collision resistance. That's my assumption. Now I want to argue, if I assume that the collision resistant is T secure, namely even someone in time poly T cannot cheat, then I want to argue, suppose there exists we're gonna get back to this, okay? What exactly this is. And we'll see it actually needs to be quite big, but we'll see that. Suppose there exists a poly T cheating prover, P star, that cheats. Namely that, and there exists, like for every lambda, or there exists like a bunch of X lambda, not in the language, and there exists a non-negligible epsilon, such that the prover succeeds with that probability. The probability that P star talking to verifier on input X, the verifier accepts him, is at least epsilon, such that for every lambda. This is, be precise, this is X sub lambda, and they get lambda. Okay, so suppose a cheating prover, for any lambda, he chooses some X sub lambda, and P star and V accepts him, even though X lambda is not in the language. Okay? My only assumption is that X lambda is smaller than 2 to the lambda. So I choose my security parameter so that the security parameter is bigger than log the size of X. Okay. Then, actually, it's not even needed for sound. This actually was needed for completeness, because we only had completeness for these X's. For soundness, actually, it doesn't really matter. Okay, so let's see. What do I want to do? I'm saying, suppose there exists a cheating prover, and this cheating prover convinces. Okay, now let's see, what did this cheating prover do? He committed to he hashed a PCP. Now I don't know what he did, he's a cheater, but he gave me a hash of something, should be a PCP. Then he opens this PCP. So what do I want to do? I want to argue I can find a collision. Why can I find a collision? What is the idea? The idea is the following. I'm going to run this cheating prover. I'm going to ask the cheating prover, okay, here's a hash key, give me a V. Then I'm going to run him many times and many PCP verifiers. I'm going to tell him, okay, you know what? Here's I1 up to IL from the PCP verifier. Give me openings. Again, here's I1 up to IL. Give me openings. Again, I'm going to kind of rewind him and try to give him tons of kind of messages I1 up to IL. So I'm going to kind of rewind him. Okay, so again, what do I want to do? Given a hash key, okay? Given a hash key, I want to find collisions for this hash key. How do I find collision from this hash key? I'm going to give this prover the hash key. He gives me a value V. Then I'm going to tell the prover, I'm going to choose a random R. I'm going to tell him, open these locations. He opens. Good. Now I'm saying, okay, actually, let's rewind him. Forget that I sent him these. Let me give him R2, different R, open. Okay, and forget R3. I'm going to run this step tons of times. R1, R2, R3, R4, a lot of them. And I'm going to have a lot of openings from him. I'm going to run it so much that I'm just going to have tons of opening. Like I'm going to run him more than like poly 1 over epsilon and more than poly 1 over epsilon and n. So the point is I'm going to run it much more than the size of the PCP times 1 over epsilon. But if to the third, whatever. I'm going to run a lot of times. Now, what's the idea? The idea is the following. If there are no collisions, look, I'm going to run. Now, if at any point, every time that he gave me an opening that didn't work, it's zero, it like didn't work, okay, so I'm going to throw it out. That, okay, look, he only succeeds in probability epsilon. So all the times that he didn't succeed, okay, well, failure. But 1 over epsilon of the time he succeeded. And in all these times, in all these 1 over epsilon, epsilon of the times he succeeded, and in all these epsilon times, I got a lot of good openings. Now, let's look at all these openings that I got. If somewhere there's a collision, I found him. I found a collision. So I'm happy. If nowhere there's a collision, then essentially I found a PCP from him. I completely constructed, like, maybe not the entire PCP, but a lot of it. And the rest I'm going to put zeros. I'm going to say, no, okay, these I didn't succeed, zeros. But the argument is that if there were no collision, I got a PCP that's accepted with probability at least poly in epsilon, which is not negligible. So that's the high-level idea, but let me say everything I said now slowly, okay? So suppose I have a cheating prover that succeeds in convincing for x not in the language. I'm going to find a collision to the hash function. So we're going to construct adversary A that breaks the collision resistant, or the collision resistant property. Okay, how do I break the collision resistant property? Here's the idea. So A, okay, so he's given a random hash key, and his goal is to find collisions. How does he find collisions? What does he do? He gives, so here's what A does. First, compute V, which is P star on hash key. That's the first thing. I got a V. Then I do the following. Many times, so for I goes from 1 to up to poly in n and 1 over epsilon, so many times, what I do is I run like what P star given HK and he gave V would run on input Ri. Ri corresponding to a, okay, let me call this J. J corresponding to a kind of I1 up to IL. I just didn't want to confuse this I with these I's. Okay, so I'm going to run many times. I'm going to choose many R's. Oh, I didn't say, sorry. Choose, sorry, for I goes to 1, choose a random Rj. So for J, go from 1, 2, up to poly in N and 1 over epsilon. I choose a random Rj. How much random bits? Like the PCP verifier. I'm going to behave like I'm going to give it the randomness of the PCP verifier, corresponding to I1 up to IL, and I'm going to compute his answers, which is pi I1 up to pi. These may be malicious answers. I denoted by pi, but of course it can, I mean, it's not necessarily corresponding to a nice PCP. He's malicious. And opening. Okay, so this is how I find collisions. I get a hash key. I give it to the cheating prover to get a value. Then, for m times, for j goes from 1 to m. M is going to be poly in n and 1 over epsilon. What do? I choose randomness for the PCP verifier, and I tell the prover, what are your answers for this randomness? With the same v. I didn't change the v. Okay, so he gave me a v in the second message, and then I kind of run the third message with him many times, m times, and expect to see answers. Okay, now what do? Those for which the row doesn't work, like those for which row doesn't accept, you know, it has a bad, the verify doesn't, this doesn't accept, I throw out. Then it's meaningless. He could put whatever he wants, I throw it out. But that's only epsilon fraction of them. Because turns out the prover, I assume the prover is accepted with probability epsilon. So epsilon I throw out. Okay, but I chose much more than 1 over, okay, this only affects, you know. So except for these epsilon, the rest are good. Yeah, sorry. I throw, as I said that, yeah. I'm left with epsilon. Okay, I throw out 1 minus epsilon, I'm left with epsilon. But epsilon is good enough because I chose more than poly 1 over epsilon. That's why I have here 1 over epsilon, because epsilon are bad, which is why, okay, so I still have a lot left. Okay, so now what do I do with the ones I have left? So I want to argue, so here's the claim. The claim is that, let me write it here. So the claim is that I should be able to find collision. So the algorithm A, what it does, the way it breaks, and so find output a collision if one exists. I'll write it here, why am I? Output, so 3, output collision if one exists. That's it. So I got, what do I mean if one exists? Many of the I's here, I asked many times, right? Because I did poly in N. N meaning kind of the witness length, yeah? More than, like, think of the witness length to the power of the third, divided by epsilon, like the size of the PCP divided by epsilon to the third. That's how you should think about it. Or to the times, like, security parameter. Okay, so now what's the point? The point is, I saw the same I many times, because I asked many queries. Now, I want to argue that so there's two options. Either every time I ask for an I, if he gave me a valid opening, it's for the same one. Or at one of the I's, he gave me valid openings, 1 for 0 and 1 for 1. If that's the case, I won. I found a collision. And then I broke the hash function. So if you believe you cannot break hash function, then you cannot break, then the scheme is secure, which is kind of what we're trying to do. But now you can say, but maybe you didn't find a hash function. Maybe you didn't find a collision. Maybe the cheating prover, whenever when he answers correctly, it's always with the same, like for every I, if he answers correctly, it's with the same pi I. He never answers correctly with pi I being 0 and with pi I being 1. Then what happened? I take all the things that he asked me and I piece together a PCP from him. So why I say, okay, so the question is, suppose that a collision happens with negligible probability. If it's not negligible, I won. I'm done. Okay, I want to argue that. Now, if not, if a collision, so if a collision occurs thank you. With negligible probability, then I want to argue I can come up with a PCP. Then there exists a pi that I can construct from this adversary such that V PCP of pi accepts with non-negligible probability. And that's a contradiction, because I assume that my pi is sound. Soundness holds with probability, you break soundness only with negligible probability. So I'm going to argue that if the probability of finding collision is negligible, then actually I can come up with a PCP that's accepted with non-negligible probability. But X is not in the language, so that breaks that can't happen. Because I know the PCP has soundness, negligible. So that can't happen, and therefore, I must have collisions with non-negligible probability, and hence broke the collision. So why is it the case that I can find a PCP that's accepted? Because what am I going to do? Remember, let's think I never found collision. It's negligible, so for all practical purposes, never. Okay, let's think of the fact we never encountered a collision. So then what do? I take this PCP. I take this adversary, I run it. Oh, I start piecing up a PCP. I say, oh, pi 1 here, good, pi I 1. Every time I ask it again, I know he'll give me this answer, because there's no collisions. And I start kind of slowly piecing together an entire PCP. Now, there may be some places of the PCP that he will never open correctly. Never. He'll never give me a valid opening. Then I don't know. Moreover, there may be some places of the PCP that somehow this verifier never asked. That can also be. So I'm going to write all the places that actually opened, I'm going to write down. Whatever didn't open, look, this adversary can always, let's say, it can always take 1 minus epsilon fraction of this PCP and never open it. And the rest open correctly. Because he's only accepted with the epsilon, right? So there can be always, I don't want to, not really 1 minus epsilon of the PCP because we ask many queries, but there can of course be some parts of the PCP that he just never answers. And it's okay because of this epsilon. Okay, so in that part, I'm going to put wherever I don't know, I'm going to just put zeros. Okay, but this is my PCP. And that's it. Now, this is pi. I'm going to call this pi. Now you're asking, why would the verifier accept pi with non-negligible probability? Well, because this P star is accepted with probability epsilon. And this, if V is going to ask, okay, so what's the concern? The concern is, well, V now is going to ask, like, places that are 0 here. Right? So the point is, we're saying, you're going to say, look, P star succeeded, maybe P star succeeded, but here, if P star succeeded and we have here pi's, then this will succeed too, because it's P star answers like this. But you're saying, but maybe here there are zeros. Maybe here there are zeros. But why are there zeros? Let's remember, why did I put zeros here? Because P star failed on them. That's why there are zeros there. I asked this place many, many times, and every time P star said no. So he won't succeed on this. Or there's also another option that VPCP never asks that question, in which case he still won't ask that question. Okay, so again, the claim is that this PCP will be accepted with probability close to epsilon, because the probability that we will hit locations where we fail, and he succeeds is very, very, very small. So whenever we fail, he will fail too, with very high probability. Because if he succeeds, then we would have succeeded. We asked so many questions, we would finally get the right answer. That's the high-level idea. Okay, I don't want to go into more details. I can send, there's a link in the website exactly on the proof. But there's two reasons I don't want to go into more detail. First, because it's tedious. So if if you're interested, just look at the paper. But also, this is not the right proof. This is not the right proof. And why is it not the right proof? Because note, I cheated you actually. I actually lied. I promised you that I broke soundness, but I didn't actually. There's a very minor, I don't know if to call it bug, but I lied. And this doesn't quite break the collision resistant with my, okay, when I say A breaks the collision resistant, I need to say A break, poly T lambda adversary that breaks, right? I said, I assume T lambda, that you cannot break the collision resistant time T lambda. So I said, let's just say there's a T lambda time P star, and I'm going to break I'm going to find the collision in time poly T lambda. That's what gives me a contradiction. Right? I argue, my assumption is that there exists a collision resistant hash that cannot be broken, collisions cannot be found in time poly T. To break that, I need to say if there exists a cheating prover, then I can break the collision resistant in time poly T. Now, let's look at the runtime of this adversary. The P star is of time poly T. That's okay. But what does my adversary do? My adversary, he tries to generate an entire PCP. And then he says, if I succeeded, I can't succeed, and therefore I must be collision. But to generate an entire PCP, he needs to run in time poly in N. What if T of lambda is smaller than N? Now, you can say, come on, T lambda must be bigger than N, otherwise this kind of, I don't like this definition, because we should allow the cheating prover to run in time poly N. If you don't, something's wrong with the definition. I don't know, maybe yes, maybe no. I have now a definition that says, time T of lambda. Maybe you want T of lambda to be smaller than N because the application makes sense. Because you use it in a way that actually the prover will never run in time N. So, I have now some T of lambda. How it connects to N, I actually don't know. And I want to ensure that, I can break the adversary, I can find collision time T to the lambda. But actually, I run P star, which is time T to the lambda, that's fine. But I run him N times. 1 over epsilon is fine, because epsilon is like epsilon in lambda or T to the lambda. Okay, it's 1 over poly T to the lambda. Fine, that's good, T to the lambda. T of lambda, sorry. But this N can be bigger than T of lambda. So really this works if, this definition is good if, only if T of lambda is bigger than N. So this is a good proof if and this is kind of bother cryptographers, because even though it makes sense to assume that T of lambda is bigger than N, it makes sense to let the cheating prover run in time poly N. It's annoying that we need to do that. So I think we should take a break, a 5-minute break. After the break, I'll tell you just a very high-level idea. There's a beautiful paper that came in 2002 by Barak and Goldreich that they showed how to get around it, how to do it for NET. They get around. They actually don't construct an entire PCP. They do what I think is a clever and more beautiful kind of what I think of as the right proof for this. And we'll see that after the break, and then we'll do the construction of the collision resistant. But there was questions before? Yeah.
Like, is the rewinding necessary? Like, could you get like lower success probability but still like polynomially?
Great question. The rewinding for, okay. So the question is the rewinding necessary? And it's a great question. The answer is, for all I know, yes, the rewinding is necessary. This question was very important also for post-quantum because, so today we're worried about quantum computers, and if the cheating prover is a quantum device, you can't rewind him because once you measure a quantum state, it collapses. And, so proving post-quantum security of this protocol, it was proved. Actually, it's known to be post-quantum secure. But it was a lot of work because it was work that required to kind of rewind the cheating prover in the quantum, like to rewind a quantum cheating prover. And why can you rewind? So they showed you can actually do it. But just to answer your question, do you need to rewind? Yes. We don't have a straight line proof of soundness for this protocol.
And is it like because you need to be able to construct a PCP when you can't?
The other proof I'll show you after the break, it doesn't quite construct a PCP, but in order to find collisions, we need to run him at least twice. I run him and then, because how am I going to find collision? I give him queries, he's going to give me answers. How can I find collisions from that? But if I run him once and I run him again with, the idea is I'm going to choose like a random query I. I'm once going to run him I with some queries, and then I'm going to run him I with other queries. And the only way you can cheat is if you're not always consistent. But at least I need to rewind you twice. So that's the. Any other questions? Yeah.
Could the right proof be simpler if we have this concrete hash function instead of this abstract notion?
No, I don't think actually when you look inside the hash functions, it just becomes messy. I think actually abstracting out the hash functions and just thinking what property gives you makes the proof cleaner. Put it to put boxes around things, and just modularize kind of what you need actually helps the understanding and simplifies the proof. I think that the problem with this proof is that it requires constructing an entire PCP. And sometimes you're saying, why do I need to construct an entire PCP? So the other proof kind of shows that you actually don't need to do that. And that's why the prover doesn't need to run time linear in n, just runs in time that depends on t. Any other questions before the break? Yeah?
Just to clarify, n here is the size of the PCP, not the size of n.
Yeah, you're right. N is the size of the PCP, but I'm thinking because I'm thinking of 3SAT, I'm thinking the input, the instance n, the witness, and the PCP are all Pauli related. So it's because I have your polynomial, it doesn't matter. But I do want to say, in some settings, you can think of the witness can be much, much smaller than the instance or much, much bigger than the instance. So for example, take non-deterministic time t. X is of size n, but the witness is of size t of n, which can be super polynomial in n. Then this becomes polynomial in the witness. The PCP is always, the PCP is always polynomially related to the instance and witness. Now, sometimes the witness is bigger, sometimes the instance is bigger. And the relation does not need to be polynomially related. If they're all polynomially related, it doesn't matter here because I put a poly. But sometimes the witness can be much, much smaller, like a log clique. The witness is size log squared, but the input is n. And sometimes the instance can be small and the witness can be big. So what I mean here is input plus witness length. Here I just put one of them because I assume 3SAT, they're both the same. So yeah, but that's a good, what really I need to put here is PCP length. That's the truth. Yeah, great point. Fantastic. Other questions before we break? Okay, let's do a 5-minute break and then we'll return.